A U-tube manometer is a mechanical device used to measure pressure. It works based on the principle of fluid mechanics, hydrostatic pressure. Um, Here is a schematic of a U-tube manometer. As you can see, there's a U-formed tube here. One side of it is open to atmosphere, the local atmospheric pressure. That's piece of A. I mark them like that. Then the other side is the unknown pressure to be measured. This is this side. Okay. The pressure signal from here goes into a device that actually shows, with the gauge and everything, that shows it has a dial and it shows the pressure itself. But the principle in which a manometer works is pretty simple. There is a liquid inside this tube. Usually it's Hg, and there is a difference in pressure between piece of A and P, and that would cause the liquid in one side to rise, and it is going to be, the level of the liquid would be higher than the other side. Namely, the unknown pressure to be measured is P, the local atmospheric pressure is piece of A, the density of transmitting fluid is marked here as rho sub F, and the density of manometer fluid here is marked as rho sub M. So these are the density of the transmitting fluid and the manometer fluid. Depending on what the fluid is, these densities would be different. So they're not a constant value. So in equilibrium, the pressure of the two columns must be balanced. Why? Because after the initial pressure, then since one side of this tube is open to the atmospheric pressure, then the level will not rise or drop unless we have a change in pressure. So at equilibrium, this equation, a piece of A plus rho sub mgh is valid. This is equal to P plus rho sub f g h. Again, these are based on the principles of hydrostatic pressure. And every time we have a column of liquid as such, the pressure would be rho sub mgh. That is anywhere at a point h at the bottom of this tube. So if we want to measure the pressure at this point inside the tube, the pressure would be rho, which is the density of the fluid, multiplied by g, multiplied by this h. Okay, and that needs to be added to that needs to be added the P sub A, which is the pressure of the atmosphere. So when we add P sub A, which also present right here at this surface, right, slightly above that, then P sub A need to be added to the hydrostatic pressure, which is at this point that I just marked in red. Perhaps I can mark it in green now at this point, and this is going to be rho of the liquid times g, which is acceleration of gravity, multiplied by h, which is the height of the column of the liquid above it. And that should be no surprise based on the principles of fluid mechanics. So after setting up this equation, again, I'm going to switch to green now. After setting up this equation here, P sub A plus rho sub mgh is P plus rho sub f g h. Then we do some algebraic manipulation really on this equation. I take a P sub A to the other side of this equation, and we would have P minus P sub A is rho sub mgh minus rho sub fgh. Remember, rho sub m is the density of manometer fluid, and rho sub f is the density of transmitting fluid. So as we are going through this equation, please keep that in mind. So we simplify this one step further by factoring GH out. It's going to be rho sub m minus rho sub f. So P minus P sub A is GH multiplied by, open parentheses, rho sub m minus rho sub f. This is the equation that would be very useful. Again, I highlighted this equation already, but I'm going to encircle it in red so you know that this is a very important equation to work with here. Okay, but that's the equation. There's also sensitivity of the U-tube manometer. U-tube manometers are sensitive, are sensitive devices, and there's also error associated with them. But the sensitivity of the U-tube manometer is simply defined as H divided by P minus P sub A. So it is H divided by delta P. So the height, as marked here by H, and when you divide that by the differences in the pressure, that would give us the sensitivity of the manometer. So H divided by delta P is going to be simply replacing delta P, which is P minus P sub A. We're going to replace that by G H rho m sub rho sub m minus rho sub H, and then the H would be from here. The delta P is this equation here. So what we are, I'm going to mark this by a little star here. Okay. So all we did was the delta P, which is nothing but P minus P sub A, would be replaced by G H multiplied by rho sub m minus rho sub f, and the H would pretty much cancel each other out, and we are going to end up with 1 over G multiplied by rho sub m minus rho sub f. This is the sensitivity. So obviously, if the value of rho sub m is very large, if the remember rho sub m was the density of the manometer fluid. So if it is if the density of the manometer fluid is much higher than rho sub f, and then in that case the rho sub f, this subtraction simply becomes rho sub m. This is going to drop out, and the sensitivity would be 1 over G rho sub m. What was rho sub m? Rho sub m was density of the manometer fluid, and rho sub f was the density of the transmitting fluid. Okay, so that's for the U-tube manometer. Let me talk about well type manometer. They are pretty similar to U-tube manometer, but the shape is different. The principle in which they work is pretty much the same. P sub A, again, there's a tube here. It still looks like U, but at the end of that, there's a little reservoir that you can see. The liquid is pretty much shown here by these lines here, by the sketches that I provided here, by the shaded areas. So one side of this is exposed to air, P sub A, and the other side is the measure P to be measured. So it pretty much operates in the same manner as the U-tube. It has a different construction. We are going to use the same principle. P minus P sub A is GH rho sub m minus rho sub f. This is equation number 1. I mark it as 1. So usually we don't measure H. Instead, we measure H prime. And H prime is H minus H prime divided by A1 over A2. So the way it actually works is we usually measure, in this case, we usually measure H prime. And then from there, we need to go back and measure H. So if H prime A2 is H minus H prime A1, and this should be easy to see, H would become H prime multiplied by the parentheses that's shown on equation 2. And that is really simple algebraic manipulation. So then I'm going to insert equation number 2. Instead of H, I'm going to replace H by H in equation 1. I'm going to replace it by H prime and the rest here shown down here. So this H prime multiplied by parentheses, it's going to go and actually replace this H that I provided you up here. Okay. So we're going to replace that. So P minus P sub A would be G H prime, and A2 divided by A1 plus 1 multiplied by rho sub M minus rho sub F, right? So in practice, the manometers, the well-type manometers that are used to measure pressure, they have certain kind of a gradual scale, and that would pretty much take care of the H prime, the effect of H prime. More information is available from your textbook. How do we measure the sensitivity of the well-type manometer? It's simply L divided by delta P, 1 over G rho sub M minus rho sub F sine of theta. This is for the general sensitivity that I just show it by an arrow here. Okay. Okay. If the manometer is inclined at an angle theta, which always it's not going to be always pretty much placed the way it is. The sine of theta would actually come into play here, and that is to take care of the inclined angle theta. Then in that case, H is measured, fluid displacement along the incline, and H would be L sine of theta. This is if we tilt our well-type manometer into some angle. Let's say if you can show this, if it gets everything gets tilted this way, of course everything would be tilted this way. If it gets tilted by an angle theta, this is the angle of tilt from the center line to center line. If it is being tilted by an angle theta, then the way we measure H would be L sine of theta, and that makes sense, right? Because if you take the sine of such an angle, you would see that you would take care of that component. So let's go over two practice problems that I prepared for you here. So the first practice problem, there is a schematic shown as such. I put it in a red, put it inside, I enclose it with a red line. So this figure is given, and we would like to find pressure at a point P sub 1. So this point P sub 1 is at a depth D from the surface, and it's pretty much underwater, a distance D. So what we simply try to do here, we assume point P1 is at datum, and what we do is the distance of that datum from the surface is measured by D. All we want to do, we wanted to see what would be the pressure at point P1, knowing that here it's exposed to a P sub 0, which is the atmospheric pressure of that particular location. So for the given figure, find P sub 1. D is given as 10.33 meter. We're going to use the equations that we have discussed so far to calculate that. The first thing we do is P sub O plus, or P sub 0 plus a rho of water, GH H sub O, which is what we really don't have here. We're going to replace that by D, is P1 plus rho H2O G H1. We're going to use the same principle. We're going to get down to this equation down here, and we simply, in this case, H1 and H sub O is not given. The difference is given, which is D. And so P1 would be P sub 0 plus a rho of water times G times D, and knowing that P sub O is the P of ATM, or the atmospheric pressure, shown here by P ATM, and that is 101.325 for that particular location. And this is also given in the problem. If it is not given, the 101.325 should be used, or 101.4 if the location is different. But 101.325 is a typical number that can be used every time the hydrostatic pressure is present, and we need to add the P atmosphere to that. So from here, the P1 would be the atmospheric pressure, the pressure at this point, which is right at the surface, which is the atmospheric pressure. We add that to rho G times D to get the pressure at P1. That's really what we do. This is the rho of water. This is the density of water, 1,000 kilogram per cubic meter. That means if we have 1 meter by 1 meter by 1 meter cube, and if we fill that with water, if you fill it up with water, it's going to weigh 1,000 kilograms. Okay. You can actually do a simple test to measure this. You can reduce this number, have a cube of 1 foot by 1 foot by 1 foot, and do the conversion and measure the weight of that, and you know how heavy water actually is. So it's 1,000 kilogram per cubic meter. We can also do another type of test. Get a gallon of water, buy it from the grocery store, and weigh it, and then you know the volume of that, and you can pretty much calculate the weight per volume for that particular liquid. So this is the density of, and then you can calculate density. So this is the density of water. We simply multiply that by 9.81 meter per second squared. That's the acceleration of gravity, multiplied by D, which is given in the problem as 3.33. And the answer would be P sub 1, 202 times 10 to the power 3 Newton per square meter. And that is pretty much 202.65 kilopascal. Remember, Newton per meter square is nothing but Pascal. So please keep that in mind. Okay. So let me go over the second problem here, the second practice problem. A single column mercury manometer, mercury Hg, right? Right. A single, this is G actually, H and G. A single column mercury manometer is used to measure the pressure in a tank. If the deflection of the column is measured as 20 centimeter, what is the corresponding tank pressure and what is the gauge pressure? The rho of mercury Hg is given as 13,600 kilogram per cubic meter. That means 1 cube by 1 cube by 1 meter by 1 meter by 1 meter of mercury is going to weigh 13,600. Whereas if you compare that with water, the water was 1,000 kilogram per cubic meter, the one that we just discussed up here. So from 1,000 kilogram, we go to 13,600 kilograms. So you can see that mercury is much heavier than water. 13 point almost. If you divide that by 1,000, it's going to be 13.6 times heavier than water. So first thing we need to do is we need to find the corresponding tank pressure. Then we need to find the gauge pressure. And as I'm going over these problems, you're going to be exposed more to some of these concepts that you may be a little bit rusty on, or you haven't, you don't remember all of it from your physics and so on. So P sub A is P sub B plus rho GD. In this case, this is for mercury, rho sub Hg times G times D. Again, G is the acceleration of gravity, D is given. It's that depth that in this problem it is shown as the pretty much depth of the single column mercury manometer. So remember up here that we just defined the P atmosphere, that is the pressure of the atmosphere at the local area. Usually we assume that as 101.325. If that's not given, there are that number P ATM would actually vary as we get higher. That pressure would be less, and again, it's important to be familiar with those. So in this case, the P sub B is P of atmosphere 101.325 or 101, that's kilopascal, 101.325 kilopascal, or 101.325, 101,325 Newton per square meter. That's the same as 101.325 kilopascal. P sub A is I add that P sub ATM, which is the atmospheric pressure. We add it to the rho GD, which is 13,600 kilogram per cubic meter multiplied by 9.81, acceleration of gravity multiplied by 0.2. Do a simple calculation, and as a result, P sub A would be 128 kilopascal, as shown here, or it's going to be 128,000 Newton per square meter. Okay, and then we need to find out what the gauge pressure is. Remember that we already added the pressure of the atmosphere to this in this equation up here. The atmospheric pressure must be included. That is shown here as P sub B, which is equal to P ATM. So we mark it as P ATM, P of atmospheric. Simply, we are going to subtract that from here and to get the gauge pressure. Again, absolute P is what we have calculated down here. And then we're going to subtract the atmospheric pressure here. So don't get confused. What we just did here, although we call it P sub A, it was actually P sub ABS. So it's really the same. This is absolute P, okay? So P A B S, okay? So don't get confused. This is also the same as P of absolute. So from that, we subtract the atmospheric pressure, P sub ATM. We subtract that, and that would give us the P sub gauge. In other words, if we did not add the atmospheric pressure to this equation, if we don't look at this one, and this, if we cross that out, the P sub A would be the gauge pressure. If we take the atmospheric pressure out of that equation, okay? All right, so that brings me to the end of the topic of manometers, and make sure you guys practice the problems that I just went over once more to get yourself familiar with that. And if you have any questions, let me know. So we would continue, our learning continues, so it is just, it goes on. Thank you.